welcome back to this video. So today we are going to treat the center mock, a question that was proposed by a student on our YouTube channel. So let's get started. So the question proposed were question 1, question 3, question 6b, c and e. Okay, so we are going to pass through the solving of the questions. Okay, so we are going to do this in different videos. So let's begin with the first. Okay, number 1 says explain why an equation that is dimensionally homogeneous may be incorrect. So this can simply be due to the presence of dimensionless constant, the presence or absence of dimensionless constant. For example, t is equal to 2 pi root L on g and t is equal to root L on g. So you see the presence of 2 pi, the absence of 2 pi in equation 2 still makes it to be homogeneous, but it is not dimensionally correct because theoretically when it is derived it is 2 pi that makes it to be correct. Now the EMF E of an induced in a coil of n turns and cross-sectional area E rotating in the uniform magnetic field of strength B with a constant angular speed omega is given by E is equal to omega NAB sine omega t. Okay, so show that the equation is homogeneous. So what will be to show that the equation is homogeneous? It suffices for us to show that the units of E should be equal to the units of W N A B sine omega t. Now what do we deduce? Now let's begin with the unit of the left hand side. So that is the unit of E. Let me write it as such, left hand side in brackets, unit of E. So what do we have? For the unit of E, what does E represent? E is the EMF, and the EMF we can use the work done per unit charge. But I always say work done is math, that's the force times distance divided by charge, which is it. So this means the units of E will be equal to, mass is a base unit, so that will be kilogram, acceleration meters per second squared times distance meters, all of this divided by the ampere second. So this simplified will give us the kilogram meter squared per second cube per ampere. So that's the unit of E. Now let's use the unit of the right hand side, that's the unit of omega NAB. So beginning with, let's begin units of right hand side. So now let's start with the units of omega. Now in circular motion, or simply omega is equal to 2 pi f. 2 pi is a dimensionless constant, so it means the unit of omega is equal to the unit of f. So this means what was the unit of f? The hertz, and the hertz is the per second, so we are going to have it as the per second. So that's the unit of omega. Units of n, dimensionless. N represents number of turns, so n is dimensionless. N is dimensionless. Next, units of E. What does E represent? Of cross-sectional area E. So unit of E is a meter square. And lastly, we have the unit of B, so of magnetic field strength B. So let's calculate the units of the magnetic field strength. Now the magnetic field strength, units of B, we can use that it's equal to the unit of the force per unit current length. So this implies that the units of B will be equal to the unit of F, kilogram meter per second squared divided by ampere times meter, and this will be simplified to be the kilogram per second squared per ampere. Now let's now combine what the units of sine omega t is a constant, is unitless. So trig functions, log functions, exponential functions are unitless. So it's clear because the unit of omega is a per second times the unit of time, which is a second, so it's unitless. So then we now compose now our units to see if it gives the unit of a right hand side. So so therefore units of omega NAB sine omega t will definitely be unit of omega per second times unit of n 1, unit of a meter square, unit of b kilogram per second per ampere, unit of sine omega t nothing. So this will give the kilogram meter square per second square per ampere. So we verify with the units of the right hand side. There we have per second cube. Where do we omit something? False. It's per second squared. Sorry, this is the per second squared. Thank you. Here we have per second cube. Okay, so you see that the base unit of the right hand side is equal to the base unit of the left hand side. So here we have kilogram meter square per second cube per ampere, and here we had kilogram meter square per second cube per ampere. So since units of the left hand side is equal to the units of right hand side, then our equation is homogeneous. Okay, so we'll just do the question on mechanics. Question number 3. Okay, question number 3. Figure 1 shows a non-uniform rod XZ of mass 1.53 kg, length 1.5 meters, and held in the position by a length of string YZ. A mass of 5.1 kg is hung at Z. The center of gravity of the rod is 0.4 meters away from X. Wow. So we'll call this O. We'll call this G. So this distance is 0.4 meters. Draw a free body force diagram of the rod. Okay, so this is our rod. I will indicate it just on this diagram. So this is our rod. So at the center of mass, at the center of gravity, we have the point of application of the weight, which is the mass of the rod times G. Then the next thing is we have the tensional force here, T. This angle here is 50, here is 40 degrees. Here we have T. We have two components of the tension. The first component, here we have T, and that's only let's resolve all the system at once. Here we have T, there will be T equals 40, and the vertical component will be T sine 30. Okay, so what then do we have? Then the next thing which we can see is nothing else. Okay, so we have resolved the forces. So here on this our mass, we can also have mg. So that is the free body force diagram showing the forces acting on that particular object. Now from there we can calculate the force exerted by the string. So the force exerted by the string is simply the tension. So how then can we do to have the tension? Now to have the tension, we can simply use resolution of forces, and the C part says the push of the hinge at X. So since there is a push, it means that we are going to have a little displacement of this hinge, which is going to be caused by a certain force we can call P. So we'll call that P, and this will be inclined to a certain angle which we'll call theta. So that is the angle we are supposed to look for at the level of this exercise. So let's begin and let's see how to tackle this particular problem. So that's my P. That's P. Now forgive the fact that our diagram is a little bit choked up. Now we are going to resolve forces. Now the best way to solve such problems most of the times is to use the principles of moment, since we have a given hinge. Now the vertical component of our force here will be P sine theta, and the horizontal component will be P cos theta. So that's the resolution. Now the next things that we have to do now is to resolve under equilibrium conditions. Now you see that at equilibrium, the horizontal forces will balance up and the vertical forces will also balance up. Now if we balance up our vertical forces, so at equilibrium, the sum of forces in the y direction will be equal to 0. Now this means, now let's sum these forces. So we have T which goes up, we have P sine theta which goes up, and we have the weight of the rod which goes down, and we have the weight of the mass which goes down. So I'm going to call this that will be upward forces P sine theta plus T sine 30. This will be equal to, what do we have? I will call the weight of the rod to be a certain WR plus the weight of our object, I will call it a certain or the weight of the mass, WM. Now what does it mean? This we see we already have a fundamental equation of equilibrium, but we cannot solve for or two unknowns or three unknowns, T, P and theta in one equation. So we need at least 3, or if possible the ones that we can get from our diagram. So we'll call the equation 1, but since we have 3 unknowns, it will be more of a variable to get at least 3. Now we are going to resolve horizontally. Horizontally, what do we have? Here is vertically. Now horizontally, what do we have? We have that P times the cosine of theta will be equal to the component of the tension in the horizontal direction, so these components. So that will be equal to T equals 40 degrees. T equals 40 degrees. Here is 40. T equals 40 degrees. Okay. Call this equation 2. Next, what do we have? We need again an equation so that we can be able to eliminate things fast. Okay, so since we have a hinge, we can apply the principle of moments. So I'm going to take moments about my hinge. So I'm going to take moments about x. So if I take moments about x, taking moments about the hinge at x, what do we have? Sum of anti-clockwise will be equal to sum of clockwise. So the moment of P with respect to x will be 0, both components. So I will only have my weight which will have a moment 0. The distance from the center of gravity to x is 0.4. So this will be a clockwise force since it's causing my body to rotate in such a manner. Likewise, the weight of our mass will also be a clockwise force, but the tension will be an anti-clockwise force. Now the weight of this tension, the horizontal component with respect to O, is 0 since it has no perpendicular arm. So let's do that moment. So we have the weight of our rod, this times this perpendicular distance, which is 0.4. So I'm going to have WR into 0.4 plus the next clockwise moment is our W of the mass times the length of our rod, which was 1.5, weight of mass into 1.5. that will now be equal to sum of anti-clockwise moments. So the only anti-clockwise force we have here is T sine 30, which will multiply all the length 1.5. Sorry, that's not T sine 30, it's 40. Oh, we are used to 30 until. Okay, so that will be T sine 40 times 1.5. T sine 40 into 1.5. So I'll call this equation 3. So that's one of my equations of equilibrium. Now from here we can calculate T clearly from equation 3. We see that many of the unknowns have been eliminated. So what do we have? So we see from here that our T will simply be equal to W, or 0.4 WR plus 1.5 Wm, all of this divided by 1.5 sine 40. So this means our tension will be equal to 0.4. Now what's the weight of the rod? The mass of the rod was given to be 1.53 kilogram. So we have into 1.53 plus 1.5 times the weight of the mass is 5.1 kilogram. 5.1 kilogram. All of this divided by 1.5 sine 40. Okay, so let's punch that and see what it gives. Zero 0.4 times 1.5 plus 1.5 times 4 times 5.1 divided by 1.5 sine 40. Okay, so what we have is, we have all of this will be multiplied by 10. So is the weight, I use the mass. Since it's mg, so I'll just multiply by 10. So we have times about 85.56 Newton. So T will be equal to 85.56 Newton. Sorry, so this is normally times 10 times 10. Okay, now let's go to, so we have calculated the force exerted on the string YZ. Now we have to calculate the push on the hinge. Yes, we have to calculate the push on the hinge, and the push of the hinge is P, as we had. Now we can just substitute that straight in to get the value of P. Let's see. Okay, so but since we already know our tensions, we can use equation 1 and 2 to easily deduce P. So from 1 and 2, so see, from 1 and 2, let's rearrange and see what we have. Now from equation 1, we have that P sine theta will be equal to WR plus WM minus T sine 40. So we have P sine theta will be equal to WR minus plus WM minus T sine 40. That was our equation 1 rearrange. Now equation 2 says P cos theta is equal to T cos 40. So here we have P cos theta is equal to T cos 40. Now if we, this equation 2, now if we take that 1 square, equation 1 square plus equation 2 squared, we have that P sine theta square plus P cos theta square will be equal to what is on the right hand square. I will call it R square. So we see from here that we have P squared can be factored out into cos squared theta plus sine squared theta, and this will be equal to certain R squared. Now the cos squared plus sine squared is 1, so it means P squared will be equal to, now let's get let's do the numerical application. Our R squared will be this plus this, so we are adding, since we squared both, so it will be WR plus WM minus T sine 40, all of that square, plus T square or T cos 40, all of this squared. So we have our values. So this means P square will be equal to the weight of the rod, the mass of the rod was 1.53. So here we have 1.53 times 9.81. Oh, I used 10 years G. Wow. Let's please use 9.81 so that we should be very precise. Let's use 9.81. 83.9. Sorry. it's advanced level, so G is not 10, so we can use 83.94 Newton. Okay, so that's what we have. So that will be times 9.81 plus 5.1. That's the mass of the weight of the mass. The weight of the mass times 9.81 minus 83.94 sine 40. All of this squared plus 83.94 cos 40, all of this squared. Okay, so what we have now from here is that we can simplify and punch on our calculators and see what it gives. So going to our calculators, we have, let's begin with the first. Okay, so we have 1.53 times 9.81 plus 5.1 times 9.81. Then we have minus 83.94 times sine 40. Times sine 40. Now all of this goes to the power 2. So this, the first one, gives us about 122.87. Then I will just add it up to 83.94 times the cosine of 40. Raised to the power 2. Okay, so we now take now let's take the square root of the answer. So we have about so the square root of the answer gives us 65.25 Newton. So I've just taken everything, so P will just be all of this raised to the power half. So the square root of the answer, or if you actually punch, you will have that, let me remove this, you will have that P square. It's approximately 4257.588 and so on and so forth. So upon the square root of all that, so P will be equal to what they have, 65.25 Newton to 2 dps. Now we have the value of P, we can have the value of theta. Now from equation 2, we have that cos theta will be equal to T cos 40 divided by P. So cos theta will be equal to T cos 40 divided by P. So this means theta will be equal to cos inverse of T cos 40 on P. Okay, but remember, what was our T? Our tension was 83.94. So it means theta will be cos inverse of 83.94 cos 40 divided by P, 65.25. Okay, so this is what is punch. Let's see what it gives. By 65 point. So that's about 0.9854. Now we'll take cos inverse of the answer. So we have about 9.77 degrees. So therefore theta is about 9.77 or 78 degrees. So that's the value of theta for which that system will be in equilibrium. So we are going to end the video here for the first part. So see you in the next video for the next part. Thanks for watching.